Greetings. So welcome to today's session. So if we recall, we were recapping about stability in the previous class, right? So we had a broad recap of what notions of stability we are going to look at, and we recapped the criteria for bounded input, bounded output stability. So today, let me recapitulate how we quantify performance. So if you recall, we quantify performance by looking at the first order and second order system. And to be very particular, the step response of first order and second order system. The main reason behind this choice is that, like, although a system can be of higher order, we assume that the dominant dynamics, like is that of a first order or a second order system. Okay, so that is the rationale behind this discussion. If you look at a first order system, so recall that the governing equation, right? The standard governing equation for a first order system is going to be dy dt plus y of t equal to b times u, right? Where t is a real parameter and b is also a real value parameter, right? So if we take the Laplace transform and apply zero initial conditions, we will immediately get the transfer function to be transfer function p of s will be equal to y of s divided by u of s. That's going to be equal to t divided by ts plus 1. Correct? So that's what we have. And if we look at this, unit step response. So if you look at the unit step response of this particular system, what do we have for unit step response? Our u of s becomes 1 by s, right? So this implies that y of s, so Laplace output, which is p of s times u of s, that's going to be equal to b, this particular case, b divided by s times ts plus 1. That's going to be equal to b multiplying 1 by s minus t divided by ts plus 1. So if we simplify this, we are going to get y of t to be equal to b multiplied by 1 minus t power minus t by m. Okay, so this will be the unit step response of this first order system. Correct? So I'm sure all of us recall all these things. Next time, just quickly recapping these concepts. So if we plot the output as a function of time, we will immediately see that the steady state output will be B. And what's going to happen is that if we look at the output per se, it will essentially go to B as time t tends to infinity, right? So that's what will happen. And the fact is that, like, when t equals capital T, the output will be 63% of the final value, or in other words, 0.63 times B. Okay, so that is the reason why capital T is called as a time constant. Okay, so this first order system. So that's a definition of time constant. That is, the time constant of the standard first order system is defined as the time interval after which the unit step response of the system is 63.2% of the steady state value, right? And if we draw a band of at around 98% of the steady state output, this is 0.98b, and we look at what time this is reached, this will be the settling time, Ts, and that will be 4 times time constant. Okay, so the settling time, this is the settling time, that is 4 times the time constant. So, and this parameter D is what is called the steady state D, because you can observe that when we give a unit step input means the value of the input at steady state as time t tends to infinity is 1, right? And we can observe that the value of the steady state output is D. So we can see that, we multiply the steady state gain and the steady state input value, we get the steady state output value, right? So that's why it is called as steady state gain. Okay. So we have these two parts. So we can observe that the way we have considered this model, first order system model, it is a 2-parameter model. That is, we have the time constant and the steady state gain as the two system parameters, right? A variant of this model is the first order system with time delay, right? So if we have a time delay, what happens here? So with time delay, let's say time delay is indicated by some TD, okay? The governing equation becomes. So as we know, time delay comes in many practical systems, right? We give an input, it's not necessary that the output starts to increase instantaneously, right? An example is friction, right? Even if I want to move a desk, I apply a force. So there is some static friction between the contact area of the desk and the ground, right? So only when that is overcome, the desk will start to move. So consequently, we can observe that, like there is going to be a time delay in the system response for many practical systems. So consequently, like we need to factor that one in. So if we have a time delay, so what happens to this governing equation? Okay, so the governing equation becomes t times dy dt plus y of t, that becomes equal to b times u d minus t. Okay, so here time t is the time. Okay, so if you look at this model, what happens is that this is called by some as the first order process plus time delay model. Okay, so in some references, you may find the abbreviation FOPTD. Okay, so that means first order process with time delay. And immediately we can observe that this is a 3-parameter model. That is, we have T, T, and TD. Okay, so there are 3 parameters. This is the 3 parameters. All right. Okay. And one also important recollection is that if we take the Laplace of the input with time delay, what will happen? If we take Laplace of t minus td, what's going to happen is that we are going to get u of s multiplied by e power minus td. That's what we are going to have. Okay. So given this background, which we can immediately figure out that the transfer function in this particular case, okay, which is given by p of s, this y of s by u of s will be b times ts plus 1, which is the same as before, however, multiplied by e power minus t. Okay, so that's what we have. All right. So now there is an interesting point here, right? So here, if you look at this transfer function, so we can immediately see that the value of n is 1, whereas the value of m is infinity, because we have this e power minus tds term, right? So in the numerator, the polynomial goes to infinite order. So this becomes what is called an improper transfer function, right? So if if you recall, what is a proper transfer function? N should be greater than or equal to n, right? So with this, the way things have been written, it results in an improper transfer. So what we have is that we have different mechanisms for approximating the time delay. One common approximation is what is called as the Faraday's first order approximation. So there are multiple approximations. So let's look at the Faraday's first order approximation of time delay. So what is this Faraday's first order approximation? What we do is that we essentially take this e power minus TDS. We just write it as e power minus TDS by 2 divided by e power TDS by 2. I'm just not writing the general formulation of Faraday approximation. I'm only explaining in a very simple way. Okay, and what happens is that we expand till the first term. If you write the power series expansion of the exponential function, you get 1 minus TDS by 2 divided by 1 plus TDS by 2. This is going to give us 2 minus TDS, okay, divided by 2 plus. Okay, so consequently, with the Faraday approximation in place, the transfer function of the system can be approximated. Okay, as d times 2 minus TDS divided by ts plus 1 multiplied by 2 plus 3. All right, so that is what. So now we can immediately observe that n is equal to 2, m is equal to 1, right? So we get a proper, in fact, strictly proper transfer function. However, we can see that there is a 0 at 2 by 2 TD, right? So this is the right of complex plane. This is what is called as a non-minimum phase zero. Okay? So as we know, this is what is called as a non-minimum phase. Okay, so this introduces a 0 in the right of complex plane, and that's what is called as a non-minimum phase. All right. So this is as far as the first order system is concerned, and the corresponding variance, okay, of the mathematical models for this first order system. And what happens is that we can have these models, approximating many realistic processes, and we can use that, right? So essentially, we have, we have this. What to say? We'll also look at a project, right? So in our course, where we use this first order plus time delay model to essentially look at approximation of real systems, and then we go and look at, right? So how do we then do this in the first place? Okay, so now moving on. And we will also learn what is the impact of this non-minimum phase zero, right? As we go. Okay. All right. Any questions on this? Okay. So moving on, the second class of systems that is typically used to essentially look at the performance, right, for the class of systems and the study is by using what is called as a second order system. Okay? So second order systems are typically motivated, from mechanical vibration problems, and consequently the standard governing equation is written as follows. So recall that the governing equation of standard second order LTI system is the following. Okay, that's given by d squared y of t dt square plus 2 zeta omega n dy dt plus omega n squared y of t is equal to omega n squared u of t. Okay, so here the parameter zeta is what is called as damping ratio, and the parameter omega n is what is called as a natural frequency. Okay? So, as I mentioned, these are motivated from vibration problems, right? So, consequently, we have some baseline, physical meanings, like associated with this, with these set of parameters. Okay, so that's what we have. So now, if we apply the Laplace transform and once again take zero initial condition, what happens? We are going to get the transfer function of the system, P of s, is going to be equal to y of s divided by u of s, and this is going to be equal to omega n square divided by s square plus 2 beta omega n s plus omega. Okay, so that's what we have. All right. So immediately we can observe that the value of n is 2. So there are 2 poles. Of course, in the standard way of writing it, the value of m is 0. Okay. So, but we can always have a factor in the numerator also. But then we'll consider this standard form. So if you look at the poles per se, if we solve for the roots of the denominator polynomial, all of us will recall them. The poles, we will get them as minus beta omega n times, minus beta omega n plus or minus omega n times square plus beta square. So this is a very standard result, as far as the roots of a quadratic polynomial, right? So now, based on this, there can be multiple cases, right? So, sorry. Okay, yeah, okay. So based on the value of zeta, there can be multiple scenarios. So if we have the parameter zeta, lying between 0 and 1, okay, we have the poles, we will have complex conjugate poles, right? So consequently, zeta squared minus 1 is going to be now negative. So if we take the square root, we are going to have a negative number there. So we take minus 1 outside, so we get j and outside with complex index, and then we'll get omega n times square root of 1 minus zeta squared. So you can see that we have swapped the order of subtraction in the square root. Okay, so this term, there is omega n times square root of 1 minus zeta squared, is what is called the damped. So damped natural frequency omega d is essentially defined as omega n times square root of 1 minus zeta. Okay, and this can be written as minus zeta omega n plus or minus j omega n. All right, so that's what we have. All right, so then what happens is that, like this case, we have what is called an underdamped second order system. So this is a scenario where we have complex conjugate poles, and the corresponding second order system is what is called as an underdamped second order system, right? And physically, the nature of response of an underdamped second order system is oscillatory. That is, when we give a step input, it does converge to a final value, but then it oscillates and then converges asymptotically to a final value, right? So that's what happens with an underdamped second order system. All right. Okay. So now, moving ahead, so if the value of zeta is exactly equal to 1, then we have a pair of repeating poles at minus omega n. Of course, one thing I should say is that like when we talk about performance, we a priori assume that the system is stable to begin with, right? So that's very important. That means that the poles lie in the left-off complex plane. That is true for the second-order system that we are studying, and also the first-order system we just discussed, right? So we can talk about performance, or talking about performance is meaningful only when the underlying system is stable to begin with. So when zeta is exactly equal to 1, we have what is called as a critically damped system. So a critically damped system has the damping ratio to be exactly equal to 1, and consequently what will happen is that like it will have a pair of repeating poles at minus omega n, right? So that's what will happen with a critically damped. So a critically damped system will not exhibit any oscillation and will converge to 1, right? So, sorry, converge to the final steady state value when a step into this. So the third case is considering zeta to be greater than 1. In this case, the poles will be at minus zeta omega n plus or minus omega n times square root of zeta square. Okay, so we are going to have two distinct poles on the negative real axis. Okay, so the system is stable, right? And this system is what is called as an overdamped second order system. Okay, so the overdamped second order system typically is something like which is not advisable or like expected in practice because it is sluggish in nature. See, an overdamped system, like has the damping ratio greater than 1, but however, like the issue is that like the response of the system will be pretty slow, right? So there won't be any oscillation, but then like it's going to be very sluggish. So for this reason, by and large, like it's a rule of thumb when we design these control systems, like we tend to go for designing underdamped systems with damping ratios between zero point 0.4 and 0.8. Okay, this is only a rule of thumb. Okay, and nothing set in stone, but essentially this is a general design philosophy. Okay, okay? So that's something we need to remember. Now, how about quantifying the response? Okay, so if we go and consider the unit step response, right, of an underdamped second order system. So I leave these as exercises to you. I'm sure you would recall them from our earlier discussions in the vehicle dynamics course. So what we do is that like we use the transfer function of the underdamped second order system, and then like we can essentially obtain like the expressions for the unit step response of the underdamped second order system, right? And from that unit step response, we essentially get the various performance metrics, like corresponding to some parameters, like which can be used for quantifying, the response characteristics, right? So if you recall what happens in this particular case, so recall that the unit step response, I leave it as an exercise for you to do. The unit step response is y of t is equal to 1 minus e power minus zeta omega n t multiplied by cos omega dt plus zeta by square root of 1 minus zeta square sin omega. Okay, so this is the expression, right? So now, if we recall what happened, okay, like with this particular response, and if you plot it, so please note that if you plot the unit step response as a function of time, it is going to go to a steady state value of 1. The origin is 1. Okay, so if you plot this, this is going to go something like this, right? It's going to overshoot, going to undershoot, and then oscillate, and then right? So that's what happens. Okay, so this is the unit step response of an 100 amp second order system. Okay, so if we look at this, there are multiple parameters that can be defined. Okay, the first parameter is what is called as the rise time, TR. Which is defined as the time taken for the system output to reach 100% of its steady state output for the first time, right? So consequently, rise time, which is denoted by TR, is one performance metric, and I leave it to you as an exercise. One can essentially get this TR as 1 by omega d tan inverse of minus square root of 1 minus beta square by beta, which can be written as phi minus beta divided by omega. Okay, so this, I'm sure all of us can recall this expression, right? So, but I request you to derive that. Okay, so what is beta? Okay, so if you plot the S-plane, and we essentially mark the poles of this 100 amp second order system, what happens is that the poles will be at minus beta omega n, okay, plus or minus j omega d. So this is plus j omega d, and this is minus j, right? So now, what is beta? If we draw a line from this pole to the origin, this angle which we get, okay, is what is called as beta. Okay, all right. So that is beta. So of course, when we substitute in this formula, please note that like this should be in the form, or this is in the this is in radians. Okay, so the unit should be in radians when we substitute in this equation. Okay, so this is how we essentially get an expression for the rise time. Okay, now if we look at the some variance of the rise time, like people will also use different measures like 0 to 90%, 5 to 95%, and so on. Okay, so but for our notion, we will use it in this manner. Okay, and so this is what we will have. All right. So immediately one can observe from the expression for rise time that like as the damping ratio decreases, the rise time here decreases. That means the system becomes faster and faster. Okay, like as we decrease the damping ratio, that means that the the system becomes less damped. The response becomes faster. Okay, so which is good, but then like there is a flip side to it. Okay, we will discuss it shortly. All right. So now the second parameter that we will have is what is called as the peak time, which is the time at which the first overshoot is reached. Okay, so this is peak time. So obviously, considering the response, so this is the time at which we are going to have the maximum value of the output, right? So we differentiate the expression for y of t equated to 0, solve for it, and then take the second derivative and then ensure that the second derivative is negative to get the expression for peak time. So the peak time expression can be obtained as phi by omega, right? So that's something which we can recall, right? So once again, I request you to go and do these derivations so that all of us recap whatever we have done earlier, right? So we are going to use all these metrics as we go along, okay, in the control design process. The next metric associated with stable second order underdam system is its maximum peak overshoot. Okay, this is denoted by M subscript P. So what is this maximum peak overshoot? So the M subscript P is defined as y at Tp minus y at infinity divided by y at infinity multiplied by 100. Yeah, that expressed as a percentage. Okay, so what is y at Tp? Y at Tp is what is the value of y when the time is at the peak value, right? So this, if you simplify, we can get it as e power minus zeta pi divided by square root of 1 minus zeta squared multiplied by 100. Okay, so the peak time, maximum peak overshoot essentially can be expressed as a percentage, and the formula is. So now we can immediately observe that as zeta decreases, the peak overshoot increases. So we just discussed that as zeta decreases, the rise time decreases, which is good, right? Which makes the system response faster, right? But then the price to pay is just like the oscillations increase, right? So the magnitude of the peak oscillation increases. Uh, so that is one flip side, like of that. As we increase the value of zeta, so what will happen is that the peak overshoot will decrease, but however, the rise time will increase. That means that the system will become more sluggish. So we can see that increasing zeta, decreasing zeta has a counterbalancing effect, or counteractive effort, like in terms of rise time and peak overshoot. All right. So this is one more reason why people take an intermediate range. Like as I mentioned, we don't want to go to too less damping ratio, not we want to go to too high a damping ratio, right? So that is why we, as a rule of thumb, we design the second order systems, such that we stay in this range of 0.4 and 0.8. Okay, so that's something which is important. All right, and the final parameter that we will also look at is settling time. By default, we take a plus or minus 2 band. Okay, as far as the response is concerned, and then like we find out what is the time interval taken for the output to settle within a plus or minus 2 band. Okay? So if we take a plus or minus 2 band and draw it around the output, as far as settling time is concerned, the question that we are asking is that by what time does it settle within this plus or minus 2 band? Okay, so that's settling time. So typically by default, okay, settling time is taken as 4 by zeta omega n, okay, using the plus or minus 2 band, like as far as our analysis is concerned. Sometimes, okay, one may consider a plus or minus 5 band, which is a larger band, right? So obviously the settling time will be lower, the expression will be smaller in value. So then this is what we have. Okay, so this is the default one. Okay, so when we, as far as our course is concerned, right, if the no specification, explicit mention is given about the band, please take the plus or minus 2 band in this particular case. Okay, so I hope that is clear. All right, so that is the expression for settling. All right, so these are the 4 parameters that are typically used to quantify, like the response of second order systems using the unit step response of underdamped second order. All right. So now going back to this graph, like if we want to plot, the response of the critically damped and low damped system. So if I were to plot the response of critically damped system, it will go something like this. Okay, so it will smoothly go to the final value. Okay? So this red curve for critically damped. So one can observe that there are no oscillations, and but it's slower than an underdamped. And if you take an overdamped system, it's going to be sluggish. Okay, it will go slowly, you know. So this is an overdamped second order. So the question is, what is it that we want to design, right? So by and large, as I mentioned, if we can tolerate some level of what to say oscillations, you know, we can essentially have this system, you know, like our design to take the form of an underdamped second order system with damping ratio in the range of 0.4 and 0.8. Okay, so that's what we do. All right. Okay. So what we have done in today's class is to essentially have an idea about this, the performance metrics, right? So what I am going to, of course, I suggest you to essentially, I'm going to leave you with a couple of questions that you can ensure figure out, you know, like when you go through the notes, you know, like I suggest you to please look at the vehicle dynamics notes and then like recap these concepts and come to the next class. But I'm going to pose you some questions and then like yeah, close this lecture. Okay, so what are these questions? So the questions are the following. So the first one, once again, these are all things that we can recap. Okay, and you please go and find out what is natural frequency. Okay, damped natural frequency, the definition, and resonance frequency. Okay, so if you recall, we had discussed the measures very carefully. Please go back and recap, and you can let me know if you have any questions. Okay, so that is one thing. Okay, the second thing is just like what happens if beta is 0. Okay, that is we have we have an undamped system. So what do you think happens to the dynamic response of the undamped second order system? Right? So that's something please find out. All right. And another what to say point which I'm going to leave you with is the following. How do we? This is something which you may want to think about. How do we convert performance specification into regions of force? Regions of force. Right. Okay. So into equivalent regions. So let me explain what I mean by this. Okay, with an example, right? Suppose you try out this example. Okay. Anyway, we will discuss this, right? Consider a settling time requirement of let's say less than 4 seconds and a peak overshoot of less than or equal to 10%, right? So what I want you to think through is that like how do we obtain the equivalent region or the corresponding region of force? Okay, region of system force corresponding to these performance metrics. Suppose we will discuss about closed loop systems in the next class, right? And then like move on to different choice of controllers and so on. So when I design the closed loop system, you know, like one may give that I want the closed loop system to satisfy this set of performance metrics, right? Then the question becomes, you know, like how do we find out, you know, what is the corresponding region where the closed loop pole should lie, right? So that will be the application, you know, like that is the motive with which I am posing this question. Right? Okay. So I think let me stop here for today's session. Are there any questions?
No, sir.
Okay. So if there are no questions, let me stop recording.